Hello, my name is Trey Henry, and today we are going to talk about geomancy and software engineering, two of my favorite topics. And I just thought I'd put this video together. It's going to be unedited, it's going to be a hot take, but it'll be fun, hopefully, and maybe informative. And I'm putting this together for people who maybe have a little bit of background in software engineering and are coming to geomancy sort of with, coming to geomancy for the first time and looking at it and noticing some patterns. And also perhaps for geomancers who maybe don't have a background in programming, but maybe a little bit of an interest in programming, maybe played around with things here and there, and are sort of interested in where these two topics overlap. And I see this as a general sort of area of exploration come up in a variety of different contexts. And people ask me questions about it because I wrote GeoRatio, which is software that's a geomancy calculator. And I think it's just interesting to look at and think about. And I think one of the easiest ways to do that is to actually write some code and demonstrate sort of what's going on, if that makes sense. I am going to be using the amazing, excellent, my favorite programming language, Elixir, which it's called Elixir. I mean, obviously it's amazing. And I'm going to be using a notebook-based coding environment called Livebook, which is an open source tool in the Elixir community. It's developed by the Elixir community, which is an amazing community as well, by the way. And it just gives you a way of being able to write text and write code and evaluate it in real time. And it's just going to let us do fun things in a kind of rapid way. So let's just dive right in. And I think the first thing that it's maybe best to do a little bit of review on is numbering systems. So let's talk about numbers. We're going to stop super basic here. Us humans, generally speaking, and for very interesting historical reasons, which we won't go into here, but are interesting in a number of different factors, including all of the sort of like magicians of old overlapping with these concepts. We use a numbering system that is base 10. It's called decimal. This is, again, should be a review to most people. And so in the decimal numbering system, we have, we call it base 10, which can also be said that it has a radix of 10. Radix just means like how many numbers basically compose the numbering system. And we say it's base 10 because we have the numbers 0 through 9, the digits 0 through 9. And then once we have more than 9, and just looking at integer numbers that don't have a fractional component and not fancy scientific numbers or anything else, we're just looking at very, very basic numbering here. When we can, with one single digit, we can count from 0 to 9, but then once we want to go past 9, then we have to use another place. And again, this should all be review, but I'll just say we have this number, 1,234. And looking at this number starting from the rightmost place in the number, which we say is the ones column, we have said we have basically 4 ones. And I'm just going to completely break this down. Again, sorry if this is a little bit review for you, but I think it's good to just sort of go over this. Every now and then it's good. I think one of the reasons I like putting videos like this together is just to go over it myself. Sometimes we take a lot of things for granted and we forget about some of these key fundamental things. So we say that we have this, the rightmost column, which our numbering system goes from right to left. Kind of cool. Again, interesting history behind this, but we won't go down that rabbit hole right now. But we have ones on the very right. And then next to that, once we got up to 9, we would say that we have 10, which is 1 in the tens column and 0 in the ones column. And in this case, we have 3 in the tens column. And then we would say that we have 2 in the hundreds column. And then we would say we have 1 in the thousands position in the number. And so then if we say, starting from the right to the left, we say we have 4. We just have 4 because it's 4 ones. And then we say we have 3 tens. and then we say we have 2 hundreds, and then we say we have 1,000. And if we add all of that together, then of course we get our number, and that's kind of how we represent numbers. And the reason that I'm going over this is because now I want to talk about binary. And this might be review also for folks, but let's make this this is a markdown. I just wanted to make that look nice. Anyway, so we will now talk about binary. So in binary, our base is actually 2. And so we say the radix is 2, meaning that we only have 2 values. We have merely 0 and 1, true and false, active, inactive, something, nothing. And this is amazing. This is incredible because all of the complexity of our digital landscape, at the very least, we can say this quite factually, and I think overlapping in very interesting ways with ideas of how complexity increases over time and thinking about creation as the separation of something from nothing. 0 and 1 are these very just fundamental concepts, and everything like this video that you're watching right now, the software that it's running on, the servers that it's hosted on, everything in the digital space, including the hardware itself, to some extent, are operating on this core concept of 0 and 1. That's it. All complexity comes after the fact. And this is also interesting to think about in terms of geomancy and sort of how the 4 mothers of a geomantic chart create all of this incredible complexity that we can interpret in interesting ways and have a very deep and rich sense of every single chart that we look at and how that overlaps with this incredible unfolding of complexity and the pattern that is the unfolding of complexity. So anyway, I don't want to go too much further down that particular rabbit hole either. Otherwise this video will be too long and far too rambling. In binary, we have 2 things, 0 and 1, that's it. So if we want to represent a bigger number, let's say the decimal number 3, one of my favorite numbers, obviously we only have a 0 and a 1 to represent our number. So we can say, in our first place, we could say we have the number 1, but then we have to have, so we can say 0, 1, and then if we need to represent 2, then we need to go over a place. So our next column in our numbering system is the column 2. And then we have the 1s, and then after that we would have the 4s, and then the 8s. And so let's just, I'll just make a binary number here, again, arbitrarily. And we'll just break this down. So we have the 1s. Let's make this a code block again. And here we have the 2s. And here we have the 4s. And here we have the 8s. And so we can think of a 4-digit binary number, which can be represented, each digit is only a 0 or a 1. We have the 1s place, the 2s place, the 4s place, the 8s place. If we thought about a binary number, just using four places here, and we had a 1, a 1, a 1, and a 1, then we would have the decimal value of 15, because we would have 8 plus 4 plus 2 plus 1. So we'd have 8, 9, 10, 11, 12, 13, 14, 15. And so if we think of 4 places in binary representing decimal numbers, we would have 16, so 0 through 15, possibilities that we could represent with 4 binary numbers. Probably you can see where I'm going with this. So let's talk about the geomantic figures. So let's take a geomantic figure here, and again, picking somewhat arbitrarily. Let's say we have the geomantic figure of Fortuna Minor, the lesser fortune, the simple, happy-go-lucky, doodah, stupid-ass luck that you stumbled into and will probably stumble out of relatively quickly. That's not to say that quick, rapid injection of fortune is not incredibly important in some cases and is incredibly valuable in some cases, but also the short-lived and fickle nature of it is also interesting to think about. But again, I don't want to go down a big rabbit hole in Geomancy. We're talking here specifically about this sort of overlapping. And where I eventually want to get to with this, and kind of like the point of all of this, is when we get to what we do when we geomantically sum two figures. But so let's starting with our geomantic figure, just also as a little bit of review here. In Geomancy, we say that the figure is composed of elementally associated lines starting from top to bottom, and there's 4 of them. And each one can be either active or inactive, inactive being represented by 2 dots, active being represented by 1 dot. And we go from fire at the top to earth at the bottom, so fire, air, water, earth, moving from top to bottom. So this is the fire line of the Fortuna Minor geomantic figure, which we would say is active because it has a single dot. And then again, here we would say the air line is active as well. And then we would say the water line is inactive and the earth line is inactive. So another way of putting this is we could say that this represents the digit 1. And this represents the digit 0. Or another way that we could say it, which is just going to become important when we start talking about logical comparisons, these can also be considered true and false. 1, 0, true, false, these things are completely equivalent. Active, inactive. These all mean the exact same thing. Something and nothing. And so, yeah, so that's a little bit of background or a little bit of review, I guess, on the geomantic figure. I think that's probably as far as we need to go there. Let's write some code. Okay, that was a lot of preamble. It always ends up being more preamble than one expects. Anyway, in this beautiful programming language that I'm going to be utilizing, and is true in most programming languages, you have a way of telling the system the programming language, generally speaking, programming languages in general, will assume base 10 because they're built by humans for humans, generally speaking. So if I just say a number and I tell the platform that I'm using to evaluate this, it just says you have the number 1, 2, 3, 4. This is a decimal number. But I can do a little indication to the programming language to say, actually, I want to talk in binary. I want to give you a binary number. And so I can use this binary number that we used before, and I can say, evaluate that. And it'll give me the number 10. And the reason is because we have a 1 in the 8s column, and we have a 1 in the 2s column, and we have a 0 in the 4s column, and a 0 in the 1s column. So 8 plus 2 equals 10. And it's showing us the decimal version of this binary number, because internally it's basically saying, okay, this is a decimal number, and I'm going to treat it like a decimal number, even though you're giving it to me in binary. So this 0b prefix just says everything that comes after this b is a binary number. So that's great. Now, before we start to dive a little bit more deeply here, what I want to be able to do is, and this is going to get a little bit, we'll go in a little bit in the weeds into the programming stuff, and hopefully it's not too terrifying for anybody, and hopefully it's fun. And if it's a little bit weird and confusing, and you've never seen this kind of stuff before, that's okay. If you're interested in it, lean into it. And yeah, it's great. Programming is amazing. Anyway, all that to say, I want to be able to give a binary number like this to the computer and then have it tell me which geomantic figure this is and spit it out in a way that represent the figure in a way that I would recognize as a geomantic figure. I'm going to do this a little bit in a long-winded way for Elixir. So if there are like Elixir programmers out there that watch this video and they're like, oh, you could do this in like one line with like I'm going to do this in a very stepwise fashion to be very illustrative. So what we're going to do, so this is a pipe operator in Elixir, and it basically just says, take the thing up there and pass it into this next thing. If you maybe have seen pipe operators in other contexts. It's just it's a really nice way of not ending up with a bunch of nested code. Anyway, so I'm going to take this binary number, and actually let's, for illustrative purposes, let's potentially use what we would think is our binary representation of the figure of Fortuna Minor. And I'm going to say, so here we have our Fortuna Minor figure. I'm going to say, moving from top to bottom in the figure, we're going to move from right to left in our binary number, so that the fire line, being the first line, is also going to be represented by the first digit in the number. So we have our active fire line here in 1, our active air line, inactive water line, inactive earth line. So we basically want to turn this into a geomantic figure. Now, there's an interesting thing. So going back here when we evaluated, before we evaluated 1010, and we got the number 10. So if we evaluate 0011, we get the number 3. It's almost like that was intentional. But here's an interesting thing. If we tell the system to give us the digits of this binary number, so we can say there's an integer library. We won't go into all of the details here, but there's a function called digits, and it'll just give me the digits of a thing that I pass into it. And you'll see here that it takes 2 values. One is the integer, which is going to get passed in the number. And then the next thing is an option, which is to provide the base. So our radix for our numbering system that we want to use for those digits. So, and it defaults, this backslash says this is the default. It defaults to 10. So we're going to say, actually, we don't want to use 10, we want to use 2, because we're talking in binary here. And so if we just evaluate this, we'll just get these 2 digits. These brackets just mean this is a list of things. And we're going to say that we've got a digit 1 and a digit 1. Well, what happened to our zeros? Well, our zeros are not valuable information in this case, and so the system just chucked them. I could say, for example, that if I have the number 000000003, and I evaluate that, it's the number 3, right? But in order to represent our geomantic figure, we want to have those zeros in there. And so I'm going to do a little bit of round tripping through a few different things here. So the first thing that I'm going to do is I'm going to take the digits that I passed in, so this output of this integer digits, which is the representation of the digits that were passed in. And I'm going to, instead of having them be a list of things, I'm going to turn it into a string. And this is a string just being text instead of being represented as numbers. It's going to be represented as a textual thing, which is different than a number. I don't want to get into types. This is a very complicated and long conversation to have. But anyway, just the reason that I'm going to do this is because it's going to allow us to put those zeros back in, even if the zeros are technically meaningless to the numbering system. So I'm going to use a library that's built in called enum, and I'm just going to say join these together. And so that now I have this text representation of those 2 digits, which are represented in quotes, which is what's telling me that this is a string. Now I want to say, if the string that you give me is less than 4 digits, which is what we need to represent our geomantic figure, then I want you to give me zeros preceding the value. This is called padding. And fortunately, Elixir gives us a very nice built-in library to do this. So we have a string module as well. And with the string, we can pad. And we can say pad leading, which is exactly what we want to do. We want to, at the beginning of it, we want to add some things. And it takes a few things here. It takes the string that we're going to pad, which is going to get passed in here because of our pipe operator. And then we can specify this count. And in our case, we want to say, we want 4 of these things. And if there's not 4 of them, then I want you to pad it out with zeros. And voila, now we have a string representation of our, that looks kind of like the binary number that we passed in. However, now the next thing that we need to do is we need to split that back out again because we want to go over each one of those and we want to represent a geometric figure for each one of these digits representing one of the lines in the geometric figure. So in that case, we're going to use another function here, which is string.graphemes. And this is basically just going to graphemes, text, 2 bytes versus 4 bytes versus like Unicode, ASCII, all of this stuff is not, that is another rabbit hole, which we're not going to go into. Anybody who's into programming will know a little bit about this. But basically the string.graphemes just says, given this string, split these things up into their own items. And so now once again, we have a list, but now we've got these zeros represented in the list. And this is the important thing that we did all of that work for. And so now we just want to go through each item in our list and we want to spit out a line in a geometric figure. So in order to do this, we're going to use a built-in function in the enum. Enum, by the way, is short for enumerable, which just means something that you can enumerate over, something you can iterate over. And map, just if you're at all familiar with concepts of like map and reduce, then this makes perfect sense to you. But if you don't, then basically what this is going to do is it's going to, for each line in, or for each item in our list, we're going to do something and we're going to return something for each item, basically. So we're going to kind of, we can think of it as transforming this list of things into another list of things of the same number of items. So, but how are we going to do this? So we're going to specify a lambda, an anonymous function. Doesn't matter. We're going to say this is the thing that we want to do for each item. And so basically we're going to say for each item, we're going to say that it's a line in our figure. And this is just an arbitrary variable that I'm assigning it. And I'm going to say that in the case that we have a 0, we want to spit out a inactive line in our geometric figure. And in the case that we have a 1, we want to spit out an active line. So this is relatively easy to do here. I could just say in the 0 case, we want to say that we're going to do our super lo-fi representation again. And in the case of 1, we're going to represent our active line. And so now we have our list representing our geometric figure in theory. And if you're maybe a little bit more familiar with programming and maybe you see where this is going, you might notice that we already have a bug. I'm going to address that in a second, but let's just keep going because right now we have our geometric figure, but it's not represented in a way that we can actually visualize it nicely. So let's go back to our enum.join, but this time when we join things together into a single thing, we're going to put new lines in between, which we represent as a \n. And this basically just says, I want to add another line in between each thing. If we evaluate that, then we get this, and we're like, okay, well, that didn't really do much. Well, the reason that didn't do much is because this is a very programmy sort of way of saying like, well, here's your string and here's what it actually contains. But what we actually want to do is we want to format that string for output on the screen, basically. And so we have a nice IO library, which stands for input output, and it has a put string function. And voila, we have our figure. But wait, that's Fortuna major, not Fortuna minor. What happened? Well, if you were paying attention, we operated, when we were dealing with our number, we were going from right to left in smaller value to larger value. But then when we had our list, we're actually operating on the list from the start of the list to the end of the list. And so what we need to do is we need to reverse the items in our list in order to get them to line up with our expectations of how the figure should be represented. And in that case, I think we just have an enum.reverse. Oh, I don't need that. And that should do it. And there we go. Sweet. So now, in theory, I should be able to pass just about anything in here that could represent a binary number between 0 and 15 in decimal, and see a geometric figure come out. So this is great. But in order to actually get to the conversation about geometric summing and how that works, and to kind of represent that in code, what I actually want to do is I want to encapsulate this code here so I don't have to kind of copy and paste this everywhere where I want to say, here's my binary representation of a figure, now give me the visual display of that figure. I'm going to encapsulate this into a function. So in order to do this, I'm going to define a module, and I'm just going to call it Geomancy. And then inside of this, I'm going to define a function, and I'm going to call it show figure. And here we're going to take the we're going to pass into our function the binary representation of the figure that we actually want to display, and I'm going to call that fig_val, meaning the value of the figure value. If you don't like my variable names because you're also a programmer, then suck it, make your own videos. No, but seriously, you should always name things in a way that makes them very easy to understand. But also, I'm being kind of quick and doing something kind of fun and quick here. Also, it's illustrative. Anyway, moving on. So let's take our code here, and I'm just going to plop that right in here, which is not going to do a very good job of formatting for me, but that's okay, because I can format it. And then instead of operating on our, hard-coded, as we would say, binary value, we just want to pass in the value that we get from our, that we receive in our function. And then, so I just evaluated that module so that now it's sort of like loaded into my session here. And then I can say geomancy.showFigure, and I can pass it a binary representation of a figure, and I should get the figure out. Woot! That's great. So now we can move on to the exciting topic of do we need another markdown block here? Nah, let's just go into code. We can now begin to talk about what we're doing when we geomantically sum two figures, which is really at the heart of it's one of the things that's at the heart of the incredible, beautiful complexity of geomancy. And how we start to overlap understandings of patterns and meaning on top of these sort of core concepts of just multiple lines of zeros and ones. And in order to do this, so when we talk about summing two figures, and this is terminology that comes from much older texts, where we say we sum two figures, and when we sum two figures, what are we actually doing? Like how are we doing this? Like how do we understand this? So let's give an example. You know what? Actually, I'm going to do a markdown block here. And let's give an example. So if we take our Fortuna minor figure and we sum it with, and I'm going to represent this as just a little, let's be even more explicit, just a little arrow going to the right here. And I'm using that because, as you might be aware, when we say we're summing two figures, we're not actually adding them together. But what are we actually doing? So let's say that we're going to sum our Fortuna minor with, don't put a period in there, I don't like that, with populace. And if you're familiar with geomancy at all, you might know that populace, while representing a group of things and a people, it's also kind of an amorphous mass, and it doesn't, every line is inactive, so it kind of also represents this sort of the still pond or the mirrored surface that reflects anything back off of it. It's this completely inactive mirror of sorts. And in this mirror sort of fashion, anything that you geomantically sum to it will result in the figure that you tried to sum it with. And the way that we get to this is we go line by line. Anybody who's familiar with geomancy, this is, again, going to be review. And we say, and you might have learned this in a number of different ways. You might have learned this in like some sort of logical true false kind of narrative. A lot of people learn it from adding them together and then adding the dots in the lines together. And then if it is an even number, then you say that it's active. And if it's an odd number, then you say that it's inactive. So you'd say here 1 + 2 = 3. And then we say that 3 is odd. And so therefore we get what? Therefore, we get a single line. And again, same thing, 1 and 1 plus 2. And here's where, sort of you can kind of understand the summing sort of idea, because you are, in this particular way, which I think is a relatively old way of kind of thinking about how you geomantically sum figures, you are adding the number of dots together and then saying, but then there's this extra part, which is it odd or is it even? And this is interesting. So we say here 2 and 2 this is even, and so therefore we end up with our 2, and then again on our earth line, like that. And so then we could say that Fortuna Minor summed with populace equals Fortuna Minor. And any figure that you pass to populace, because of the way that geomantic math works, will result in the figure that you put into it, which is a magical mystery about populace. And there's a lot of interesting things there. Anyway, but if we're not summing, then what is it that we're actually doing here? And this is where, going back to our discussion earlier, where we were talking about the geometric figures, and I was adding this sort of like 1 and 0, and I also added this true and false. And this is because I'm going to jump to the punchline here and say that it's an exclusive OR. And if you were trying to figure this out on your own, then you might go to look at some patterns of logical sort of operations. If you have a programming background, this would make sense to you. If you don't have a programming background, you might be like, what the hell are you even talking about? And I think that it's probably easiest, and I already loaded this up. This is the Wikipedia page. I almost said the Wikipedia page. It's a pity, this Wikipedia page, on exclusive OR. And there's some really nice little diagrams here, and there's a little explanation here. Exclusive or exclusive disjunction, don't call it that. Nobody calls it that. Maybe people whose business is logical operators. I don't know. I've never heard it called an exclusive disjunction. Is a logical operation that is true if and only if its arguments differ. One is true, the other is false. And okay, and then there's a bunch of other stuff here. Let's come down to the very aptly named truth table. This is just a table of truth, which is great. And we can say that if we have false and false, then an exclusive OR should say that a value exclusively ORed with another value that is false will result in false, because they are the same. And if we have false and true, then it would return true. If we have true and false, then it would return true, because they're different. And if we have true and true, then it would return false, because they are the same. And if you look at this chart, that's geomantically summing. I almost said summoning. That's a different thing. So this is what we're actually doing. We are performing a exclusive OR operation on each line in each of the figures, and this is what results in our resulting value. And unsurprisingly, probably to you, we have a very nice way in Elixir, and this is true in most programming languages. Many programming languages will provide a way to provide what are called binary operators or bitwise operators, which give you these abilities to do things like exclusive ORs. So we have, I think it's just called bitwise, yeah. So we have a bitwise exclusive OR, and it'll take two values, and then it will return a value, which is those two values exclusively ORed together. And so we can say we have, for example, let's take our Fortuna Minor figure as we represented it in binary. And, keeping in mind, again, now we know that this evaluates decimally to 3, and so I could actually represent this exactly the same way here, and that's exactly what the system is going to do. But I'm just going to leave it like this for the purposes of it looking sort of correct. And then we're going to pass in populace. And what we would expect to get out of this is the output of this should be the number 3, which is the decimal version of Fortuna Minor, right? And there we go. We can see that it is. So before we go too much further with playing around with the bitwise exclusive OR, probably what we want to do is to sort of create a just something here that'll like kind of nicely print out our evaluation of two figures. So I can just say I'm going to put using my little library here. Actually, before I even start with that, let's say let's just assign a couple of variables here and just say that we have Fortuna minor, which is this, and populous, which is this. Just assign a couple of variables so that I can just refer to them by name here. And so I can say, do my show, and I'm going to say, because I'm going to start with Fortuna minor. And I'm just going to comment this out for a second. We'll just make sure that that works, which it does. And actually, we don't even need to do this iota puts because we did that already. And then we're going to, but now we are going to do that because I'm going to actually just put a string to the little window here, and I'm going to say this, and geomantically summed with, and then we're going to take our, we're going to do show figure again, and we're going to say populous, and then we should see that it spits out populous, and then we're going to say equals, and then we say, ooh, what's that? One moment. I'm just going to finish the video and record real quick.
Well done, but I interrupted that.
Yeah, that's fine. I can edit it out. Husband just came home from work. I'll edit that all out. So, yeah, so then we're saying that we have our Fortuna minor figure geometrically summed with our populous figure equals, and then we'll uncomment our line here. And instead of passing in these values to our exclusive OR, we're going to say that we're going to take Fortuna minor, and our next, and the thing that we're going to sum it with is populous. And of course, we want to also, because this is going to result in a value, and we want that value to be represented as a geomantic figure as well, we're going to say that we have our show, we're going to pass that into our show figure, which of course we can just do this way as well. And so then we say that this figure, Fortuna minor, geomantically summed with populous, equals Fortuna minor. And so now we could fiddle with these values, but before we do that, let's just also put this up in our little library here. And we could just say that we have a function called pretty sum, and it will take a figure value 1 and a figure value 2. So it'll take our two figures. And basically, it'll just do this pretty printing. And instead of operating on these variables that we defined earlier, we're going to say that we're going to operate on our values that we passed in. So we're just going to say whatever the first value is summed with whatever the second value is equals the bitwise exclusive OR of those two values. Yes? And then, so we can go ahead and evaluate that. And then coming down here, we can just get rid of all of this. And we can say, now we have another function in here called pretty sum. And we can say Fortuna minor and populous. And we get the same thing. And so now we could also say via equals this. And then we could geometrically sum Fortuna Minor and Via. And if you're familiar with Geomancy, then you would know that Via, where every line is active, is the great changer. Instead of being the reflector, it takes anything and it shifts it into its opposite. It's sort of figural opposite. It shifts everything. It changes everything. It's a figure of change. And so when we pass in Fortuna Minor, then we get out the figure Fortuna Major. And so in this way, we could, potentially pass all of the 16 geomantic figures to this function and spit out every combination. Or we could play around with this in other ways. We could use this as the start of a geomantic calculator. There's a whole thing built into Elixir Livebook called Kino that gives you very nice ways to print things. And I almost went down the rabbit hole of just being like, oh, I could put this into a table and actually create a shield chart. And then this video would be even longer than it is now. So hopefully this is interesting, kind of what's the whistle on some of these topics. We talked about binary numbers, what we mean when we geomantically sum two figures. It's actually a bitwise exclusive operation. So you could be a super nerd in your next conversation with other geomancers and be like, well, actually, you're not summing the two figures. Actually, don't be that guy or girl or person. But anyway, yeah, just some coding and thinking about fun things. And I love this stuff. And for those of you who are maybe interested in this and also love it too, I do hope that this was interesting and not a waste of your time. And if you ever want to talk about these things, I think the best real-time way of getting a hold of me is on Sam Block's excellent, well, I guess it's not just Sam Block's, but the Hermetic House of Life Discord, of which Sam Block is a key person and potentially there's a whole history there. Anyway, whatever, it doesn't matter. The Hermetic House of Life is a place where you can find me. I generally lurk there. I'm not frequently engaged there because I find voluminous Discord communities like the Hermetic House of Life, there's just a lot going on there. So, but if you at me there, and I think I'm just Trey Henry on there, then I will get a notification and I will hop into a chat, and I'm always happy to talk about these things and to answer questions about them. And, if you're a person who's thinking about, you want to write your own geomantic calculator and maybe the language of your choice and use that as sort of I think it's a really great learning opportunity. It was a lot of fun, especially when you start to get into some of the more complicated aspects of geomancy, like like perfections in the wheel chart, for example. Or even doing things like evaluating the via puncti, like how do you recursively go back through the chart and figure out what the source of a particular thing is. Relatively easy to do with your eyes when looking at a chart, but telling a computer how to do it is an interesting way. I think anybody who has a little bit of an interest in these two topics, it's worth trying to write your own geomancy calculator. And it's certainly a tried and true tradition for geomancers to do. Anyhow, that's it. Okay, I'm going to stop rambling. I hope you're all amazing and well, and that is it for this episode. And I will see you next time.